most self-improving systems don't fail because the idea is wrong. They fail because they are mutating the wrong thing. If the auditable surface is too broad or too narrow or too vague, the loop gets noisy. Very easily, it loses the clarity, and the rollbacks start into guesswork. So the lesson focuses on one thing, defining the genome. Once the mutation surface is clearly scoped, every decision that follows will become easier and absolutely reasoned to about. So here's the first thing. At the high level, think of this course as a one bounded system. Each lesson adds a mechanism, but the earlier contract or earlier lesson is always running underneath. So I would recommend, if you haven't watched lesson 1, give a go at lesson 1 as well to make sure you have a connected and in-depth context. However, if you understand this concept, please continue. We will have a small recap in a hands-on session as well. Lesson 1, we establish the core contract, the mutation surface, one fixed judge, and the evidence trail, and an end-to-end run to understand how the overall context could look like. The AutoGen, the choice of our framework, sit on top of the orchestration scene, not on the correctness boundary. That's important. This lesson builds directly on the top of that foundation. We are not restarting. We are extending where we left the same mutation engine by defining the pipeline genome more precisely. So keep the full system in mind from the lesson 1, and we'll have a quick recap in hands-on as well. Everything from earlier lesson is still active, and this piece will only add some more work because the structure is already in place. Here is the things to narrow down. From a full loop genome that fits a single file, that's what makes keep autonomous mutation actually reviewable instead of just looking impressive. However, I must tell you, in some real cases where you might have multiple genome files in a one scope solution. We do have. But that's very much based on architecture by architecture and case by case basis. So don't be afraid if there are multiple genomes, and don't be afraid if there is a single scope genome. They both work as long as the case is sufficient to make those calls. A failure signal only useful if it maps clearly something fixable, and that's what this lesson is all about. How to identify what is fixable. We just don't want to draw a sort of an infinite wish list to LLMs to fix it, because that will most likely lead to hallucination and incorrect and overpressing LLM influence over the data. So we need to first understand very quickly that what is fixable. A bounded genome turns the vague issue into concrete difference that loop can actually act upon, and that's what saw in the lesson 1 hands-on as well. How does it pick it up? Each and every use cases or each and every riff cases during generating genome. Giving the genome file 1 isn't just a model friendly, it's actually human friendly as well. But as said, it could be multiple as well. It's easier to inspect and easier to find a diff in a Git, because Git is also underneath a part of our solution, and it's a part of the rollback strategy. And it's easier to reset, as I said. Trust comes from trying every difference to a measurable outcome. That's where I think majority of the mutable agents do fail. How do we measure a mutation? Is it just a binary success or failure, or is it something the quality of a success or failure? Well, we'll cover that in a later lessons as well. But here it's important to understand this is the one of the core principles. That's why we will make such a choices. The outcome panel and the trust signal make it possible to evaluate changes based on the evidence, not on the intuition. So the core idea is pretty much simple. Failure lands on a single scene. Difference stays small. The results are measurable, and that's what makes genome safe to evolve. Now, let's open the genome file in our hands-on lab where we go straight now, and make sure you have the GitHub checked out. The link is in description below, or comments wherever you're watching this particular lesson. And it would be useful to be ready beforehand we start the hands-on lab, so you can pause and get everything ready for you. So that's it. Let's go on Visual Studio Code and let's figure it out from there. So we are on the Visual Studio Code. I would this time, last time I suggested to start with README. This time I would say, because the lesson 1 gave you a good understanding of what our CleanLoop hands-on look like, so you can actually start from the lesson 2 itself. And here is the preview of lesson 2 I have created. So it would be easier for everyone to just quickly go through this to understand. And if you are only coming from this video itself, you can actually go on a lesson 1 to give a quick read. Now, where we left, this was the whole example, and we left here. You can see that the fast waning trigger. What it says, the failure signals, the next chapter. And at that time I said, just leave it there. We'll pick it up in the next chapter. And this is what the flow of the first lesson. And I'm sure that you have finished those exercises as well. Give or take some advanced exercises to make sure that learning has actually happened across. Now let's go back on a lesson 2 where you see the failure signals coming from there through the focus lens, which I already discussed. So I'm not going to waste time here. That's the execution flow. You can actually go in that file, which is in the architecture, and let's load the execution flow. So which has all the execution flow across the our core base. So this is a master execution. This is how the actual flow look like for the full clean loop example from lesson 1. Lesson 1 hasn't got any much sort of a execution flow. From lesson 2, it will help you to understand. So the process happen is 5 inputs have been read by this particular function. So you can actually go and quickly look the function as well. Normalize the numerical amount. That's kind of what we call it, a deterministic analysis where it's happening and trying to understand what is fixable and what is not fixable, because we want to keep bounded context not just in limit of physical file, but also understanding what we are trying to solve with it. We are trying to not solving a problem of a universal data engineer using harness or AI agents. We are particularly looking for a use case where financial series are having discrepancies in the formats, shuffling in the row, and inconsistent CSVs. We are particularly focusing on that problem. So the boundedness, the bounded context or bounded mutation is not about bounding a physical limit of a file. Of course, that's part of it, but it's also about bounding it towards the functionality and what the problem we are trying to solve. That's a very important distinction everyone need to understand when they make this word meaningful. Say bounded mutation, it's a bounding from physical aspect of it, it's a bounding from a problem and solution aspect of it. So we are looking for certain problems and solution. Now whatever is fixable using a deterministic, make a decision, yes, we can fix using a deterministic, and then it will go and fix those things deterministically. But those areas which are non-deterministic, and it's very difficult to fix by the if else or the kind of a complex conditional loop. So to solve that problem and to give a little bit of beginning space, as I said, what is software 3.0? It's a cavity wall, 2 strong brick layer. Between that there is a wriggling space or the middle hollow space where things can actually shuffle, make a right decision how to handle it. For example, if the outside it's very heated environment, the middle insulation, the cavity wall, will ensure that heat does not transmit directly on other side of it. If it is a single brick wall, it would. On the same side, if we got some noisy party going on inside the house, the cavity wall will also ensure, because of the absorption of audio waves, and it could reflect each other, and outside it won't be that much, people won't be able to hear that much, and that's the benefit of it. So what it does, it solves that purpose. It fixes the mess in between. And that's the same thing whenever the data comes through, or they can use the same principles whenever we're sending data to someone. The limit of contract flexibility is available as that wriggling space, and that wriggling space, or that middle hollow space, is filled with the AI, where the AI can make those decisions. And that's where we are choosing what scope of a problem, and those mutation playbook which were generated by LLM itself based on the mutation we have identified, and those mutations will be fixed. So 25 mutations were fixed by the playbook, which was generated using the LLMs, and then added to the master CSV, which is basically our output file, and it looks pretty much simple. So let's say it's looked pretty much structured, yeah. And what mutation failed, that generated a signals. But I already shared you the better way to access it, which is Streamlit dashboard, which will open it later. And some baseline score that teaches you when functions we will run. But I would say go and have good read about it before we go. I have left some of the code anchors here. You can see I have left some of the code anchors. You can take them and just see what those code anchors look like. Sorry, just a minute. Probably using wrong shortcuts. Anyways, the clean data runtime here, what it does, you have some sort of a understanding the file as a learner facing endpoint, and this is where the actually deterministic loop basically start. This normalization, which is the mutation playbook, however, this normalization actually start first as a deterministic. So it try to normalize using a deterministic approach. If the amount text does not normalize, then try to resolve the mutation rule. Once it start resolving the multiple mutation loop, and those mutation rules are available in basically data set. So we have already defined what are the mutation rule, and this is what the bounded does is. So we providing mutation hint along with the prompt and the skills, and of course you can add more things as you want as a context. There's nothing stops you how to use LLMs, but I'm keeping it simple using a mutation hint and action. So that's how the mutation playbook actually get generated, which we saw here. Sorry, that's something we saw here in execution flow, isn't it? Yes, the mutation playbook, and then mutation got fixed. So that's where we are basically. See the code, read the code, and understand what is happening. The export writer, it's say in this order. If you go in this order, export writer 2 and 2, it explains how we actually generate those exported values as well. So let's go and basically see if we got status valid. The first command status, just to check everything is configured. Yes, Microsoft V4, and there is a reason why I'm using the lower end of LLM is because this approach is very useful if you can actually host local or a cost-effective LLM interfaces. However, if you got a use case where you want to actually use more advanced LLM, then always prefer that whichever fits your case. So you don't have to just consider like, okay, it's better to go for SLMs or medium or large. It's a case by case basis, but because I use this, because I prefer, I'm not doing that complex operation which require additional intelligence that I have to pay for. So I'm using it. And in my organization as well, the 90% of our self-correcting loops and all this software 3.0 are basically SLMs, and those SLMs are actually hosted by us using our own infrastructure in cloud, and it's most cost-effective way to handle it. So let's see, it's working fine. Brilliant. Let me just go and verify it so we make sure that our LLMs actually connects. Oops, sorry, wrong connectivity. Okay, let's see, everything fine. and then I'm going to reset it. Well done. So it's connecting. Let's reset. Hopefully reset is done, and let's call the evaluate. So last time we called the loop. Loop will make it run end to end. Evaluate will basically come to this point of example that we saw. So we can see here what it did. It actually passed all the mutation planning and everything that what it found. It matched the 30 what we expected. It missing the 25 from the gold validation, and then it generated the particular a genome file. So you want to see here genome file is in actually it runs dynamically. So so that code is not actually saved. That's what we are not doing that in this particular example, but you can always use the work trees. Work trees are the better option for production implementation. We use work trees, so it always create a work tree, run the work tree, and or roll back the work tree whenever it needs. Don't go with the branches, otherwise you will inflate the git history a lot. The work trees are better. It runs locally and then it just destroy itself. Or if we need to check in, then we bring it in and we keep the mutation alive. Or we can actually adopt that mutation into permanent starter point as well, as a starter genome as well. So that's more thing is called something is called the habitual learning. So once you understand what is a habitual learning from the mutation can actually also make autonomous decision how to change the genome starting point. So apparently our genome starting point is very simple, a deterministic point, but in future if you find that these are the repetitive offenders, then behavioral learning is very important as well. It's a slightly different from a reinforced learning. We'll pick it up in the later stage because there are many different approaches and strategies you can apply. In this course, we'll keep the core mutation at this stage, but I'm gonna do more courses where we would do behavioral mutation using the prompt mutation and the skin mutation as well, which is both in terms of adopting the behavioral mutation along with the core mutation as well. So there are 3 or 4 different advancement of this particular pattern, and we'll take it one by one as we finish the courses. But this is what our hands-on look like. I would also recommend you to go for exercises in this case, which is start with simple, go how far you can go and reset as many times you want. And from a dashboard point of view, you just run this command util.py dashboard and that will bring the dashboard. Here, just a minute. Browser, just opening browser, and this is our dashboard. So you can always go through here. It will have all the sort of data quality validations which we have found, and it will provide you everything that you need. So yeah, that's all for this particular hands-on session. Let's go back to our labs and see what remaining parts we need to discuss. Well, okay, so let me go back to the labs. Okay, welcome back. At this point, the genome is clearly defined. The loop now has a concrete place to apply some pressure, and you have a boundary that you can defend. And as I said, the boundary is not just physical, but also the functional, especially from problem domain boundaries as well. Next lesson, we will fire up the orchestrator, and that's take the failure evidence and turn into the candidate mutation, verification and selection, because it look the judge and everything else as well. And then once it has been validated, whether we decide whether we accept it or reject it, I mean to say retreat it. So we'll discuss that in detail with the orchestrator, but thank you very much for joining and I'll see you in the next lesson.